Hi, we are from Group C and we will present about the gift free energy. This is our member in the Group C.
Selamat sejahtera kepada doktor. My name is Yap Ji Yang. Right now, I'm going to present the thermodynamic definition and significance of Gibbs-free energy. So Gibbs-free energy, which is denoted by G, is equal to U plus PV minus TS. U is internal energy, PV is work done, and TS is just temperature times the entropy. If we use the definition of the enthalpy, we can change it into H minus TS. H represents the total heat content of the system. TS represents the energy unavailable to do work due to disorder, which is entropy. G is the energy remains in the system after we minus the Ts. So if we take the total differential of the equation, we'll get dG equals negative S dt plus V dP. So this equation reveals the natural variables of G are temperature T and pressure P, which means if you want to change G, we have to change its temperature and pressure of the system. So in nature, the nature actually favors the minimization of G. If the delta G is smaller than zero, the process is spontaneous. If it's not, if delta G is greater than zero, and if the delta G is equal to zero, the system is in equilibrium. So phase shift happens when G is minimized, like particle change from solid to liquid to gas. The Gibbs free energy is minimized. However, the equation above, which the dG equals negative STD plus VDP, works only in a closed system. To know how G is connected to the quantum gases and grand canonical example, we need to introduce the chemical potential mu. So chemical potential mu. So if particles are allowed to flow, which become an open system, the equation earlier becomes dG equals negative STD plus VDP plus mu dN. If we using this equation, if we differentiate G with respect to N and let P and T become constant, the thermodynamic definition of U is shown here. So chemical potential represents the energy cost or gain by adding a particle to the system while T and P remain constant. However, for a single component system, the Gibbs free energy is simply equals to mu times N, or mu equals G over N. So for a pure substance, the chemical potential is simply the Gibbs free energy per particle. So chemical potential mu actually acts as a driving force for particle flow. The particles will flow from a region of high chemical potential to low chemical potential to minimize G. This flow will continue until mu is equalized. In phase equilibrium, it means that, let's say, a system is changed from liquid to gas phase, it's the chemical potential of liquid will equal to chemical potential of gas. That's all for my part.
Derivation and interpretation of grand canonical partition function. We define system equal to reservoir plus subsystem. Then the total energy of system U equal to U sub R plus U sub S, and the total number of particles N equal to N sub R plus N sub S. The reservoir is massive, so we assume that the subsystem energy and particle count are much smaller than the total. For the entropy expansion, the probability of finding the subsystem in a specific state is proportional to the number of microstates available to the reservoir. Using the Boltzmann definition of entropy, we can express this multiplicity as an exponential function of entropy on equation 1, and then we substitute 1 into 2, then we get equation 3. So we use the fact that energy of subsystem and number of particle of subsystem is very very small to the total, so we use Taylor expand. So we have entropy sub R equal to entropy sub R bracket U minus U sub S and N minus N sub S. So we obtain equation 4, which S sub R Un minus delta S sub R over U sub R times by U sub S minus delta S sub R over N sub R times by N sub S. So we apply standard thermodynamic definition for temperature and chemical potential. We have equation 5 and 6, and we substitute 5, 6 into 4. So we obtain equation 7. So 7, entropy of reservoir equal to entropy of reservoir bracket Un minus energy of subsystem over T plus chemical potential times by number of particles in subsystem over T. So we substitute 7 into 3, and then we get probability of reservoir bracket energy of reservoir equal to exponential negative beta times by energy of subsystem negative minus by chemical potential and number of times by number of particles of subsystem. Then we normalize the constant. We use Gibbs distribution. Then P equal to 1 over Z exponential minus beta U sub S minus mu N sub S equals to 1. So C equal to 1 over summation of exponential equal to 1 over Z. So we get Z equal to summation of expansion negative beta times U of sub S minus mu times by N sub S. For the interpretation of grand canonical potential function, derivation begin with an open system in contact with a massive reservoir that maintain a constant temperature T and chemical potential mu. As these two entities exchange both energy and particle, derivation reveals the Gibbs factor which dictates the probability of system being in a specific state depends on U minus mu n. Here the chemical potential acts as the kind of particle pressure that aligns the system internal energy against the reservoir tendency to push particle in or out. The resulting grand potential function Z serves as a statistical blueprint that sums every possible configuration of energy and particle count into a single normalization constant. Ultimately, the bridge to the macroscopic world is formed through the grand potential omega equal to Boltzmann constant T ln Z, which for most industrial fluid is interpreted simply as minus PV. This is allow you to connect the quantum behavior in individual particles directly to measurable industrial properties like the pressure in a tank or the carrier concentration in a semiconductor.
In this part of assignment, I will explain the difference between Fermi-Dirac and Bose-Einstein statistic and how the chemical potential influence the particle occupancy in quantum system. First, Fermi-Dirac apply to fermions such as electron. This particle can obey the Pauli exclusion principle, which means that only one particle can occupy a given quantum state at a time. The average number of particles occupying a state with energy epsilon is given by Fermi-Dirac distribution. In this case, the chemical potential denoted by mu acts like an energy bounded at low temperature. Energy state below mu are mostly occupied, while state above mu are mostly empty. At absolute zero temperature, mu is equal to Fermi energy, which represents the highest occupied energy level. Next, Bose-Einstein statistic apply to boson, such as photon or helium for atoms. Unlike fermion, boson do not obey the Pauli exclusion principle, which so many particles can occupy at the same energy state. The Bose-Einstein distribution shows that the occupation number increases strongly for low energy states. Here, the chemical potential must always satisfy the condition, which mu less than or equal to epsilon zero, where the epsilon zero is the ground state energy. So as mu approaches the epsilon zero from below, the occupancy of the lowest energy state become large. This leads to a phenomenon called Bose-Einstein condensation, where a large number of particles accumulate in the ground state at low temperature. In summary, the key difference between the two statistics lies in allowed occupancy of energy state. Fermions are limited to one particle per state, while bosons can have multiple particles in the same state. The chemical potential controls how the particles are distributed across the energy level, acting as an occupancy threshold for fermions and enabling condensation behavior for bosons.
So about the degenerate Fermi case, the fermions need to follow the Pauli exclusive principle, which they need to stay out of each other and force to the higher state, and this will cause the degeneracy pressure. And from the formula at the screen, you can see that when T equals to 0 and mu equal to Fermi energy, all of the particles will being forced available energy state, and this will create the Fermi sea. And for the real life description, pressure help the white dwarf at the right hand side, the blue one. Due to the white dwarf is extremely high density and it will have a very high gravity. And the degeneracy pressure provided by the particle will stop the white dwarf getting smaller and smaller. And if you're adding the mass, for the normal case, if you add the mass for a planet, it will become bigger. But for the white dwarf, it will become smaller because the particle will closer, so that it produce more degeneracy pressure to overcome the increase of the gravity by the increasing of the mass. Besides, for the unexpected low heat capacity for metal, it can be explained by the degenerate Fermi gas also. Because in the metal, the electron is being forced at the lowest available energy lower than the Fermi energy to create the degeneracy pressure, overcome the electrostatic force coming from the proton. So every electron is stick at the lowest energy so that it will have the enough pressure, and therefore there is only a few electrons at the surface of the Fermi sea that can be absorb energy enough to jump to higher state. However, for the Bose-Einstein condensate, you can see at the equation on the screen. So when the mu is getting higher closer to the E, which is the energy of the quantum state. So it is due to the drop of the temperature. You will see that the occupancy will be physically infinite. So this means that at the low temperature, all of the particle will fall at the ground state and share the single quantum waveform only. And this phenomena cause the disappear of the individual identity of the atom, and they behave as a single and giant superatom. So in real life, it can be used to describe about the superfluid of the liquid helium-4. So this is because at low temperature until 2.17 Kelvin, the liquid helium will become a superfluid with zero viscosity. And this is because all of the particles at the lowest energy level, and they cannot lose any energy due to the friction. So because they at the lower step, so they cannot drop to the lower step. And the zero viscosity, if you see the YouTube, you will find that the water, the liquid, will come from inside the bowl to outside because it is zero viscosity.
Hello, my name is Faris Razik and I'm going to explain about photon gases and phase transition. So for photon gases, a photon gas is a collection of photon in thermal equilibrium with matter such as electromagnetic radiation inside a cavity. Unlike massive particles, photons can be freely created or destroyed through absorption and emission by the cavity walls. As a result, the number of photons is not conserved. Because particle number is not fixed, the chemical potential of a photon gas is zero. So mu photon is equal to zero. So in the grand canonical ensemble, the average occupation number for bosons is given by the Bose-Einstein distribution, and E 1 over exponent E minus mu over KT minus 1. And for photon, substituting mu equals to 0, give 1 over exponent epsilon over KT minus 1. So for the Gibbs, free energy is defined as G is equal to U minus Ts plus PV. For the photon gas, the chemical potential is 0. The pressure arises from radiation pressure and the Gibbs free energy is minimized at equilibrium. So for mu is 0. Mu is equal to delta G over delta N. So adding or removing photons does not change the Gibbs free energy. This explains why the system naturally adjusts photon number to maintain equilibrium at given temperature. Photon are bosons and obey Bose-Einstein statistic. However, unlike massive boson, photon do not undergo Bose-Einstein condensation. This is because their chemical potential is fixed at 0 and cannot approach the ground state energy. As temperature decreases, photon density decreases rather than condensing into a single quantum state. This is fundamentally different from atomic Bose gas. Now we are moving to phase transition. A phase transition occurs when a system changes from one thermodynamic phase to another. Phase equilibrium is governed by chemical potential equality. For two phases, alpha and beta, in equilibrium, mu alpha Tp equals to mu beta Tp. This condition ensures that there is no net particle flow between phases. And during equilibrium, vapor equilibrium, G liquid is equal to G vapor. The length and heat of the transition arise from entropy difference between phases. And lastly, the grand canonical ensemble is particularly useful for describing system where the particle exchange occur and phase coexistence is present. In this ensemble, the thermodynamic potential is the grand potential. So ohms equal to U minus Ts minus mu n equal to negative PV. At phase equilibrium, the temperature, pressure, and chemical potential are equal and grand potential is minimized.